The second part of Lab 4 is about transistors. The first part of the experiments are about BJT transistor circuitry, bipolar junction transistors, and in this case we're using specifically the 2N3904 and NPN BJT, and the other part would be just a demonstration of how a Mosfet works. And in this case, for both, we'll see that a BJT is a current-driven device, meaning you have to generate a current to obtain a current, whereas with the Mosfet, it's a voltage-driven device, meaning you have to generate a voltage, or you have to have a voltage available at the input of a certain amount before a current can be generated. And the current, of course, will be visible here through a light bulb that will turn on. So in the circuit that you have in a manual, it's supposedly you're supposed to use a switch. But what I'm going to do is I'm going to just by hand disconnect this resistor from the power supply and then connect it again if need be. But before I do that, when we talk about the transistor, the 2N3904, when the flat side is facing you, in this case I can read the writing on that face, the right terminal is the collector, the middle terminal is the base, and the left terminal is the emitter. In this case, the emitter is connected to ground, as you see. The collector is connected to the light bulb, which then gets to be connected to the power supply, to the positive of the power supply. And the base is connected to the power supply through this resistor. Now, the purpose of this resistor is to control the current that flows into the base. But it is a necessity to have some resistance in that path, and the reason is that the base to emitter junction is equivalent to a diode. And you know that as a diode, you have to protect it from the amount of current that goes in it, because what happens is that as the voltage increases, the current can increase in major powers of 10, not just double, triple, but in powers of 10, 10 to the power 2, 10 to the power 5, and so on. So you could easily destroy that junction, and that's why we have to control the current that enters the base. As a base emitter junction, which is equivalent to kind of a general purpose diode, the voltage that we expect approximately is again 0.7 volts for silicon type of transistor. And so in this case, when it comes time to measure the current into the base, I can measure the current directly with an ammeter, or I can do it by measuring the voltage across this resistance, and knowing that a 5 volt is supplied, then you have a resistor, then you have a diode. If you remember 0.7 volt, that means the resistance would have 4.3 volts, and you divide by the resistance and you get the current. Now you will see also that this resistance here, the higher it is, the dimmer the current is, because the higher it is, the voltage being the same, 4.3 volts, that means the current will be lower. But if you go lower, then you'll find that it becomes brighter. But the problem here is that when we look at the BJT transistor, where I said the collector current would be higher, so there's going to be some kind of amplification of the current, and being higher, it may be higher as in absolute value, but the ratio of the collector current to the base current may decrease. So I'm doing here the measurement with something intermediary, and I'm using a 2.2 kilo ohm resistor. You can use that, you can use 1K, you can use 4.7K. And as I connect it to the power supply, so again, I don't need a switch. I just used directly my hand to make the connection, and I see that I have generated a current at the collector since the light bulb is on. And so in this case, to measure the current, I am going to remove this wire and insert the ammeter between this wire and the collector. Now the current will flow positively from the light bulb to the collector. All right, so I'm going to put my red cable here, cable, and the negative here, and I see that the current is about 99.5 milliamps. So again, I connect this one here to complete the circuit, and if I want to measure the base current, and I'm gonna do that by removing this and completing the circuit by inserting my ammeter. Again, the current is going to be positive from the power, because this green is connected to the red terminal, through the resistor. And as you see, I have the light bulb that is on, so the circuit is working properly. And the current at the base is 1.9 milliamps, so about the ratio of 50 or so. And so this is a demonstration that this circuit, specifically this circuit, shows that the transistor, this NPN transistor, works as a current amplifier. Another part of using the BJT is to show how we can use a potentiometer, which is like a constant resistance between the two outer terminals, but the middle is an arm that allows for the two resistors, as you have seen in class, or the entire resistor to be like divided into two parts, the sum being a constant. But as I turn the knob here, you will see that I vary one resistance. If I make one part bigger, the other one would be smaller, the sum still being a constant, but that means I can play with the resistances or the amount of current or the amount of voltage, therefore the amount of current that will be applied to the base. So in this case, we see that I have to make sure that it is connected properly. And in this case, as you see here, one terminal of the potentiometer is connected to ground. The second outer terminal is connected to power, 5 volts, and the middle terminal is connected to the base through resistor. Now, theoretically, that resistor should not be needed, but the problem is, if you remember, this applies a voltage to the base and the emitter junction, which is a diode. And if this resistor was absent, then if you apply a voltage much higher than 0.7 volts, and as I told you before, this current can increase in powers of 10, depending on how much increase in the voltage you apply, then obviously when we go to higher voltages, then obviously this resistor would help provide us with some protection. That means no matter what I apply, hopefully most of the voltage, and means the voltage other than 0.7 would be dropped across this resistor. And in the absence of this resistor, and if you apply directly a voltage greater than whatever the voltage is and whatever the current is at the base, obviously the transistor may break down if that current becomes excessive and higher than what that transistor, specifically this one, can handle. But the idea of this potentiometer is just to show that as I turn it and I decide how much current is applied, you see here that I can decide the brightness in the light bulb by deciding the voltage and therefore the current applied to the transistor. And so in this case, you can think of it as a dimmer, right? I can dim the current and I can dim the brightness in the light bulb with this. However, this is not the kind of dimmer you want to build for devices in the house, and the reason is that you're still consuming the maximum amount of power that is supposed to be provided. Like, for example, if you deal with a 100-watt light bulb, regardless of how much power you provide the light bulb, the potentiometer itself is going to consume that much, the maximum. And so the dimmers that you buy from the stores are a little bit more special in the sense that when the light bulb is allowed to handle 30 watts, you only pay for 30 watts. And if you increase it to 50 watts, you pay for 50 watts. No more, no less. Even if the light bulb is a 200 watt light bulb, right? You pay only for what you consume. But with this dimmer, it's not going to happen. So though I can call it a dimmer, but it's not the kind of dimmer you want to use to save money. You may dim the light, that's for sure, as we see that we have done here, but it is not the one that allows for the money to be saved. The last part of this experiment, Lab 4, is about the Mosfet. And we're going to show that it is a voltage-driven device. So before I start talking about the circuit itself, let me just say that as far as this Mosfet that you have, which is a power Mosfet, IRF10 from your kit, has 3 terminals just like the BJT, and the right pin is the source, the middle pin is the drain, and the left pin is the gate. So in this case, obviously, similar to what we did with the BJT, think of the association gate, base, drain, collector, source, emitter. So in this case, the source is connected to ground. We connect the light bulb from the power to the drain, which when we did to the collector, and we're going to use the gate to control the current flow in the light bulb. In the days when I was younger, I would just touch this wire and the light bulb would turn on. All right. Obviously, this is not happening. Maybe my body is completely discharged, but what happens is that you young people may be able to redo this experiment, and you will see that just to show that it is a voltage driven by my body does not generate any current, but theoretically if there is enough charge in my body, that would allow a voltage to be applied from the gate to the source, and that would be enough to generate the current at the drain. But in this case, if I connect it straight to the power supply, so obviously there is a current that flows now in the light bulb into the drain. And so, but just to see, look at when I remove the wire from the power, the light bulb is still on, right? And so just the static in the air or whatever it is that allows that voltage to be higher than some threshold, and the light bulb is still on, right? That means there's still a current flow. Of course, it does not mean you're getting the current for nothing. You're still paying for the current because it comes from the battery, right? Or from the outlet or whatever. But the idea here is that you don't need to generate the current like we did with the BJT at the base and keep that current flowing for the collector current to remain right in the circuit. In this case, as you see, and of course, just to show how discharged my body is by just touching it, and then I turn it off, right? Or of course I could have made sure that it is turned off when I ground the gate, right? And you see here when I ground the gate, it turns off, right? But as I said, as you see here when I remove the wire, but if I touch it by my hand, I think it's like I discharged the whole thing. All right, so that is it as far as the Lab 4 is concerned. Just remember that the BJT is current driven and the Mosfet is voltage driven.